Last episode, one tree had two readers. The evaluator read it in a value environment and produced ranked rows. The type checker read it in a type environment and produced a type or a localized error. The syntax did not change. The question we asked of it changed. That is the opening for a much stronger design. Keep the typed tree fixed. Ask it to execute, and we want rows. Ask it to explain itself, and we want a logical plan. Ask how expensive it looks, and we want an estimate. Ask it to compile, and we want a program in another language. One stable representation can become a narrow waist between many ways to author a program and many ways to use it. The reusable part is almost embarrassingly small. For an atom, ask the current algebra what that atom means. For a list, recursively interpret every argument, then ask the algebra how this operator combines those child meanings. This pattern is often called a fold. The tree decides where recursion goes, the algebra decides what comes back up.
But execution cannot evaluate the predicate before it has a row. Is this really the same bottom-up walk?
Yes, in the execution algebra, a node produces a function that is waiting for an environment, where later supplies each row to the predicate function. In the other algebras, nodes produce plan fragments, estimates, or target syntax. The result type changes while the recursive skeleton stays fixed. With the execution algebra, source reads 9 type transaction rows. Filter retains 6. Grouping produces 4 customer buckets. Sum, sort, and take return B at 520, Chen at 515, and D at 500. This is the dynamic meaning we built in episode 3, now expressed as one choice of algebra. Swap in the explanation algebra. No transaction row is opened. Each operator instead returns a phrase and connects it to the child plan. The root becomes take 3, sort total descending, sum amount, group by customer, filter the 2 conditions, then scan transactions. The explanation is computed from the program, so it cannot quietly describe a different pipeline. An estimator combines the tree with facts about the source. Our tiny model is told there are 9 rows, that 2/3 survive the filter, and that 4 groups are expected. It charges 9 work units to scan, 18 to test the predicate, 6 each to group and sum, 8 to sort, and 3 to take. The result is 50 abstract work units and 3 output rows. This is a transparent prediction, not stopwatch time. The SQL algebra never opens the source either. It emits a select with sum, the transaction table, both filter conditions, a group, descending order, and a limit. Notice that the date constructor became a SQL date literal. This compiler only covers our small language, but its output is executable target code. A different backend could preserve the same source meaning while omitting something else. 3 layers are easy to blur. The language gives the source tree a meaning, these ranked rows. The compiler translates that tree into another program, this SQL text. Then a database chooses a physical strategy for the SQL, perhaps a table scan, a hash aggregate, and a sort. Translation is not execution, and a physical plan is not the language definition. Keeping those contracts separate lets each layer change safely. We have reached the payoff of programs as data. The canonical tree is a small shared boundary, and new consumers can be added without rewriting every authoring form. But composition is still only implied by nesting. Next, we ask what it means for 2 pieces to fit. Why a Unix pipe is a kind of function composition, and what extra structure appears when real processes can fail, block, or write to more than one channel.